Ladies and gentlemen, a warm welcome to our online media briefing about our new CoolSiC 1.2 kV CIPOS Maxi IPM. My name is Fabian Schiffer and I will be your host for this event. Throughout the year, Infineon has launched plenty of SiC solutions for various industries. Today, we would like to conclude our launch activities for this year with an IPM. The SiC MOSFET integrated in this IPM makes it the most powerful in its voltage class and package. The presentation will be given by Alfred Hesner, who is Senior Director, Technical Marketing for IPMs at Infineon's Industrial Power Control Division. Please note that you can submit your questions throughout Junction or via email at webcast@infineon.com. All questions will be answered during the subsequent Q&A session, that is, following a short break after the presentation. A market news about the IPM was published today at 9 o'clock. You should have it in your inbox. This is on our website, as will be the presentation you will be going to see shortly. You will find it on our website. Should there be any questions or requests regarding press material afterwards, please don't hesitate to be in contact. Having said this, please let me now hand over to Alfred. Alfred, the stage is all yours.
Thank you very much, Fabian. Much appreciated. Hello and welcome and good morning and good afternoon also from my side. I'm Alfred Hesner, the Senior Director for our IPM products, technical marketing from Infineon. I will take you through today's presentation, which is focused on our first intelligent power module using silicon carbide MOSFETs, a very compact and powerful combination that has massive advantages for our customers' applications. There are three global trends that are really driving what is happening in power electronics to a significant extent. First of all, the massive increase of use of clean energy, like wind and sun, that are a vital part of future's energy mix. Then certainly the topic of energy efficiency. Every watt that is not wasted is certainly saved and has beneficial effects way beyond. So that enables systems that make the world greener. And the third one is electric mobility, which is electrification of mobility in both private and public transport segments. So a lot of motors and a lot of power electronics go there. And these trends can be very nicely addressed with our new technology, silicon carbide, that will enable more energy from clean resources and get more out of less energy. The technical advantages of silicon carbide are well known and have been discussed many times, like increased performance, high power density, and as a consequence, of course, reduced system size and also lower system cost due to the less effort that need to be spent, especially on the thermal design. Now, there is another development which is called intelligent power modules. These power modules integrate many components into one package, and Infineon has been in the production of these products for a very long time, especially using IGBTs. We can see here in this overview how many components actually go into such an IPM, including 6 power switches, 3 gate drivers, and quite a handful of passive components that otherwise would have to sit on the PCB, are now all integrated in one package. And that makes it for a very compact system solution that has multiple further advantages, especially time to market, since a lot of the complicated high power routing is already done. The performance is improved due to the very good adjustment between the drivers and the power switches, and reliability is also further increased. The end of our product line together, production. Here we see an overview of the entire IPM portfolio that Infineon is offering, from very small to very large power, starting on the left side with the CIPOS Nano, which is coming in a small QFN type package in low power ranges from 20 to maybe 150, 200 watts using MOSFETs. Then the next bigger family, the CIPOS Micro, for many different applications, especially in the home appliance space, like dishwashers, refrigerators, up to a power range of roughly 250 to 450 watts. CIPOS Tiny, our latest platform development that comes both in a dual inline as well as single inline package, very space saving for motor integrated inverters. The CIPOS Mini is our workhorse, has been around for a few years, and we are continuously releasing new products in that package platform to extend the power range further. And today we will be talking about the latest member of our CIPOS Maxi family. The Maxi come with a breakdown voltage of 1200 volts, so they are really optimized for three-phase power grids and more industrial type applications. This is an overview on this product, the silicon carbide IPM. It's called IM828. It is a fully isolated dual inline molded module with 1200 volt CoolSiC MOSFETs. The power capability of this product exceeds 8 kilowatt. In fact, in our measurements, we could see that it was really hard to believe how much power we can get out of this device. It has very good heat dissipation out of the DCB package construction. The gate driver we use is our own 1200 volt silicon on insulator technology that is extremely robust also against voltage spikes on the outside. The bootstrap functionality is integrated. We have a full set of protections, including overcurrent shutdown, but also cross-conduction prevention. There is an independent temperature thermistor inside the package that can be read out from the microcontroller to always know what is the temperature of the power module. And we, of course, have also under voltage lockout at all channels optimized for the use with silicon carbide MOSFETs. This device includes 45 milliohm silicon carbide power MOSFETs, only that due to the package, we are specifying them at 55 milliohms, as you can see here, at a drain current of 20 amps and a junction temperature of 25 centigrade, so room temperature. And the applications that we are targeting with this device at this point are commercial air conditioners, and here especially the active filter topology, which sits in the power inlet of this application, and we will see more about this application in a moment. Then certainly also industrial motor drives and pumps, and for example also high power fans. Obviously with 8 kilowatts there is a lot of air that you can move with those. This CoolSiC MOSFET technology offers very, very low losses, and that was one of the key features to make them implement in this intelligent power module, leading to high power density and really very high efficiency in the systems realized with this part. And this part also enables a very wide switching speed range. The switching frequencies can actually go very high, and that is used in, for example, active filter applications to create a large benefit for our customers. We will see that in a moment. Here we see a comparison of this device against a 1200 volt 50 amps IPM realized in silicon IGBT technology. And so the blue curves represent the silicon carbide IPM, whereas the red curves are the silicon IGBT. And on the lower left-hand corner, we see a diagram of the case temperature at the various operating conditions in the two operating points that I mentioned up there over time. And it is important to do these measurements on a longer term to eventually see how the devices settle thermally, which is reached in this case after 6 to 8 minutes roughly. So case 1 is operating it at 5 kilohertz switching frequency, a rather low switching frequency, which is appropriate for industrial drives, but also for large compressors, for example, and 25 amps peak output current. The second case is operating it at 30 kilohertz, and we chose this operating point because it really is beyond the capability of silicon IGBTs in most cases. And we can see that in both cases, the silicon carbide IPM actually shows lower junction temperatures and better performance, lower losses. And especially the second case with 30 kilohertz switching frequency is leading to a junction temperature that is very, very high for the competitor device. And the losses that we can see here are also very high. So that really is not a recommended operating condition for silicon devices. This is an overview of the key features of this product as they relate to what our customers are trying to achieve here. We can see it is a three-phase inverter topology with a very small compact molded package up to 8 kilowatts, embedded SOI gate driver for highest robustness, and lots of additional pins, including built-in bootstrap, overcurrent shutdown, under voltage lockout, and an enable pin so that the operation of the inverter can be controlled from the outside. The benefits that can be had from this is, of course, a minimized PCB size, making the system physically smaller. The PCB footprint design is eased as well because the power routing on the PCB is determined to a large extent by the arrangement of the pins on the package, which we have considered carefully. We are saving a lot of external peripheral components that are now integrated. A wide switching speed range, especially switching frequencies above what can typically be achieved with silicon IGBTs. We have a very good stability, certainly due to the SOI gate driver against transient voltage, over voltage peaks. Very low switching losses that lead to a reduced size of the heatsink and further system cost savings there. And of course, continuous monitoring of the thermal status of the system with the built-in thermistor. So the values that can be achieved are shown here. Fast time to market, reduced system cost, really high efficiency and high power density among the most important. And the key applications that we are targeting with this device are, first of all, servo drives for a compact system design and very good performance, especially for very dynamic load requirements. Then active filters or active rectifiers, as they are also called, for any type of industrial application with a three-phase input, including, for example, pumps, but also HVAC equipment, heating, ventilation, air condition. And then commercial aircon systems, and here especially the compressor, which requires a very compact, high power density type of motor drive to achieve the best performance out of that compressor. This is an example of an advanced servo drive topology using the silicon carbide IPM. This device really allows the miniaturization of the servo drive and support the high power requirements for dynamic load conditions, as can be seen in the servo drive's mission profiles. And here it is very important to note that servo drives see a lot of load variation, leading to a lot of junction temperature fluctuation in the power switches. And the lower the losses, the more lower are also the temperature variations of the power switches, and that enables a longer lifetime and reliability especially. And the high switching frequency possible with these devices leads to a possible higher corner frequency of the control loop for the regulation of the position of the load, and that enables much better load dynamics, especially on the mechanical side. This is another example of a advanced motor drive topology for fans and pumps. Here, the input stage, the power factor correction stage and rectifier stage is done with the silicon carbide IPM, IM828, whereas the motor inverter is now done with the IM818, which is the IGBT version of this one. You may want to ask why this strange choice of components. Very simple. We will see in a moment. For the input power factor correction stage, it is very advantageous to use the silicon carbide IPM. The high switching frequencies can lead to a significant reduction in the inductors that are needed in this stage, and a much better performance, especially for total harmonic distortion. And on the output side towards the motor, using the silicon IGBT IPM here is perfectly okay, since the switching speed that is needed for the motor is limited mostly by the isolation of the motor and the leakage current that can be allowed in the system. So typically switching frequencies in the range of 4 to 6 kilohertz for industrial systems are perfectly okay, especially for motor drives that do not require high dynamic load requirements, such as fans and pumps. So this choice here is really optimized and works together very well. Both components have similar mechanical dimensions, and that simplifies a lot the design of the heatsink. Here now we see probably the most interesting application setup. This is for larger HVAC systems, where the input active filter is done using the silicon carbide IPM, and also the same IPM is used for the motor drive for the compressor. And an additional IPM used for the outdoor fan, and this will make the electronics for such high power air conditioning systems very, very compact and high performing. And this really enables compliance with all the necessary regulations, for example the IEC 61000 and others for the harmonic current suppression. The system cost and system weight is reduced, and that way the system performance is optimized. This is an example, an evaluation board that we created to allow customers to really enable and evaluate the performance of this IPM. This board is designed, as we can see below, the power board diagram with an input rectifier, then EMI filter, and then a control interface and the silicon carbide IPM, and then a motor connector. The input voltage is regular three-phase input voltage, 380 volt AC. The output power of this little board here is 8 kilowatts. And the size of the board is only 150 times 140 millimeters. So it is really very, very compact and achieving a very high output power. And it has all the necessary features: auxiliary power supply, overcurrent protection, over temperature protection, sensing of the DC link voltage, and so on. It is a pure power board, and it needs to be operated with a separate control board. So that's why we see the example of the control board here on the right-hand side. This control board is based on Infineon's iMotion motion controller products, in this case the IMC 101. And I have brought this board as an example. In fact, it is a slightly older version of the board, so it doesn't look exactly like the one, but it's very similar. And here you can see the IPM, and the size of the new board is roughly 2/3 of this one. It is already available. And here I also brought the controller board, which will then plug into the connector, which is located here on this side. So in order to form a complete system, including control and power stage, where you only need to connect the AC input voltage and then connect your motor to this terminal here. And then in less than an hour, your motor should be operating and turning. This is all supported by our MCE Wizard and MCE Designer software that is used to configure the iMotion controllers and operate the motor parameters and everything. This is an image, a thermal image of this evaluation board, where it is operating actually at 8.9 kilowatt output power. The input voltage was 550 volt AC, and the RMS output current 11.5 amps. And we can see here the case temperature of this IPM just barely reaching 120 centigrade under the given cooling conditions here. And this picture also shows that really this evaluation board is designed to extract the maximum out of the IPM, as we can see from the temperature distribution here on this picture. And this is a very, very impressive power density for such a device. I doubt that there is a device on the market that will actually achieve a higher power density at this point. So, as a summary and a conclusion, Infineon's IM828 silicon carbide IPM is really taking us to the next level of performance here. We do have a long and successful history with silicon carbide's rectifiers and now power switches also, available in various form factors as discrete components, as frame-based modules, and now also as intelligent power modules. A very strong, powerful, and reliable technology qualified to industrial standards. And this really represents a very good option for applications that require higher performance and efficiency, that have to support high dynamic loads, very fast and very controlled movements of the motor, and then also very low power density, highest efficiency for making the system most compact. The IM828 silicon carbide IPM is the latest and greatest addition to the portfolio of our CoolSiC products. It really shows very high power density and low losses that enables system cost savings, as we have seen. The high switching frequency especially enables high performance for systems with high load dynamics, and it also enables significant system cost reductions in active filter applications. The input power factor correction, where the inductor now is no longer a huge transformer that sits off the board, but can be a much smaller inductor that can be assembled on the board. And of course, this device, as all our devices, has seen full industrial qualification and offers therefore a very high reliability and robustness. That concludes my presentation. Thank you very much, and let's move back to Fabian.
Thank you very much, Alfred, for your insights and your presentation. We will now take a short break to collect your questions. Please be reminded that you can either use the chat functionality or send us an email at webcast@infineon.com. We will be with you answering your questions very shortly. Stay tuned. So, ladies and gentlemen, thanks for having stayed tuned. There are a couple of questions which I would now like to pose to Alfred. Let me start with Ralf Higelke's questions. Is the SIO driver, gate driver, the same that is in the ICE driver ED 2023-0?
In fact, yes, it is the same driver. Well, not exactly. We are modifying it so that it works with the power switches that we have put into the IPM. Especially the driver strength on the output is adjusted. The 6ED2230 is also a 1200 volt SOI technology, very robust device, and it provides full output current, which is then adjusted with external components to whichever power switch you are connecting. This we cannot do inside an IPM. Here we have to adjust the driver output strength a little bit so that it fits the switches and achieves the proper switching speed.
Ralf, I hope this answers your question. If not, please just add a little note in the chat functionality. We do have another question from Sani Theo, and he's asking, does this module find application in electric vehicles?
Very good question. In fact, our modules are qualified to an industrial standard, not automotive at this point. And so there is unfortunately no possibility to use them in full automotive type applications. But there are multiple other applications that I would summarize under electric mobility, including, for example, autonomous guided vehicles and commercial agricultural vehicles, those type of applications. And then certainly also in systems like door control or climate conditioning in mobility applications, where this device could be very interesting. And we have actually seen a couple of requests from applications like electric aviation, where this part is considered, where especially the very low losses lead to a much lighter system, a much smaller heatsink, And for airborne type of applications, that is, of course, very, very important.
And the same participant also asks, why is it called intelligent?
Yes. We had quite some discussion about this a few years back, and there is a choice between intelligent and also integrated power modules. Both are possible. We chose intelligent simply because in our gate drivers, which constitute the intelligent part of the IPM, there is multiple functions integrated, especially along the thoughts of control and enable and system considerations that make this part more robust and more, let's say, self-protecting to a certain extent, whereas the control actually sits in the external controller. Please note that Infineon also has what is called smart IPMs. These are intelligent power modules that additionally have a motion control engine integrated, and so they are smart and intelligent. So you can judge for yourself if that makes a lot of sense. But we think that is a very clear explanation of added intelligence inside an IPM that makes this really a very easy power subsystem that can be controlled from a microcontroller with no effort.
Thanks, Alfred, for this. And there's another 2 questions which we received via our webcast at Infineon.com email. First question is, you were mentioning that using this IPM will lead to savings in induction. Can you be a little more precise or outspoken on, for example, weight, size? How does this influence the
Certainly.
solution?
I went a little fast at that point, yes. So I'm referring to the third point that you can see here on this slide. The high switching frequency enables significant system cost reductions in active filter applications. And we have been working with multiple customers on this topic in particular. The system topology that is used is an active rectifier front end. So it's, you could consider it a bidirectional converter at the input towards the grid. And it has 3 inductors in the power lines. The size of these inductors depend on the switching frequency of the power switches in the active rectifier stage. The 3 half bridges there. And with a higher switching frequency, the inductors that are used there can be made much smaller. So in this case, we are talking moving from something like 5 to 10 kilohertz to 48 kilohertz or more. And in this particular case that I'm thinking of with a customer in China, we were able to reduce the inductors from something that was about this size, coming in at over 2 kilograms for the 3 of them, and which had to be mounted off-board in the chassis, to inductors that could be integrated onto the PCB, the inductance level much lower. The high frequency losses in the inductor went down significantly as well, so that provided an additional benefit towards the losses in the system. And so the impact of this was multiple. So now the inductors are board mounted and much, much smaller, and that saved a significant assembly cost. It saved significantly on the cost for the inductors. You can imagine a piece of metal like this compared to this one is quite dramatic. And then the efficiency of the system was also increased. So there were multiple advantages right there.
Okay, we do have another question per email, and the participant is asking, you showed the thermal picture, and we've seen a junction temperature of 120 degrees Celsius. Is this of any concern?
Actually, what we could see was the case temperature.
Sorry for that.
120 degrees C. In fact, this is not a concern. You may have seen over the last years that Infineon has started to qualify our switch technologies at 175 degrees junction temperature maximum for continuous operation. And for our IPM packages, the allowable operating temperature has gone up to 125 centigrade, which is really high. And this is due to the really good robustness and reliability of our power switches and package construction that we can achieve now, that we can enable higher operating temperatures. And there is no concern at all. This is actually fully covered by the datasheet of this part and the qualification of this part that we have performed. So there is no concern there. And by the way, higher temperatures for the components actually lead to a more efficient thermal design, because the thermal gradient between the power switches and the outside world is increased. So it sounds counterintuitive, but it actually helps.
Thanks for answering this. Another question just arrived us from Engelbert Hopf, and he would like to know, can you give us a number for the TAM, total addressable market, Infineon is expecting from its SiC IPMs in the future, for example, until 2025? Now, I know that we're kind of reluctant to give away our expectations and details about specific markets, but maybe you can give us some idea of what we're expecting.
Mm-hmm. Certainly. So it is actually a difficult question. And of course, the market size for power electronics applications is well known. There's multiple market reports for those available. And there is also a lot of communication coming from Infineon showing how big is the power market and how are we participating. But for the silicon carbide IPM, the question is difficult simply because this is a market in the making. Quite a few customers are now identifying and finding out what this silicon carbide technology and the silicon carbide IPMs in particular can provide as a benefit to the application. And this is on the one side kind of cannibalizing application or products that are based on silicon, not only ours, but also from competition. And it is also enabling new application spaces that is actually increasing the market size. And this is a very dynamic picture at this point. It is not so easy to quantify what is happening there on a day-to-day basis. But we are working with all the large customers, especially in the industrial space, but also in the commercial HVAC type of business. And the volumes that we are seeing there are significant. We are seeing a double-digit million type of market size easily. In fact, pretty high and strong growth for this technology. The adoption rates are really very impressive.
Thank you very much for joining today's online media briefing. As said before, all the materials will be available shortly for download. We are looking forward to hearing from you. And in case you have questions, please don't hesitate to be in contact. With that, I would like to end the broadcast. Have a good day and most of all, stay healthy.